Hello everyone. In this video, I will be talking about one-way ANOVA. The F-test used to compare two variances can also be used to compare three or more means. And this technique is called analysis of a variance or ANOVA. For three groups, the F-test can only show whether or not a difference exists among the three means, not where the difference lies. And of course, this can apply to more than three groups. So you may be thinking, why shouldn't we use a t-test to compare two means and then compare again the other two means, and maybe we can expand that and use it to compare three or more means? Well, there is a little bit more to that. And as we go through the formulas, you'll understand why we need to use an F-test, not a t-test. The t-test, yes, is used to compare two means, and we've done that. But when it comes to three or more, we should and we will be using an F-test. And the process is called ANOVA. So how do we set up the hypothesis? This is how we set up the hypothesis. The first hypothesis is the means are equals. And in this case, we have n different populations. N is the number of populations. And H sub A is at least one mean is different from the other. This will always be a right-tailed test. The following assumptions apply when using the F-test to compare three or more means. First, the population from which the samples were obtained are approximately normally distributed. Then, the samples must be randomly selected and independent of each other. And three, the variances of the populations must be equal. If you think about this, if it's not specified in the problem that the variances are equal, then you must do a two-sample F-test to see if the variances are equal. So you should do a test of the two variances and then do an ANOVA test. Most of the time, it will be specified in the problem. But this is what needs to be checked before doing an ANOVA test. When it comes to testing three or more means, two different estimates of the population variances are made. The first estimate is called the between group variance, and it involves finding the variance of the sample means. The notation is this one, and that is called the mean square between. And if you think about it, if you have more groups, of course, there will be variation between groups. So this estimate should make sense. The second estimate is the within group variance and is made by computing the variance using all the data, and it is not affected by differences in the means. And here is a notation, and this one stands for mean square within. Now thinking of the two estimates, one which is called the between group variance and the other one that is called the within group variance. If there is no difference in the means, the between group variance will be approximately equal to the within group variance, and the F-test value will be close to 1. And if that happens, the null hypothesis will not be rejected. However, when the means differ significantly, the between group variance will be much larger than the within group variance, which means the test statistic will be significantly greater than 1. And that will lead to this decision. The null hypothesis will be rejected. So let's take a look at more formulas, and we will arrive at the test statistic formula. So just to recap, ANOVA uses the F distribution because in order to see if there is a difference between means, it gets first through the two variances. It's using this to estimate the mean square between, and it's using the second estimate, which measures the variation within samples and is using all data. The test value then, it is a ratio of mean square between and mean square within. It comes to 2 degrees of freedom. Degrees of freedom of the numerator will be k minus 1. Degrees of freedom of the denominator will be n minus k, where k is the number of individual samples or groups, and N is the total sample size. So this is how the test value for an ANOVA test looks like. And in order to actually arrive at these estimates, we have to go through the sum of squares between and the sum of squares within. Sum of squares between and is denoted SSB. It's actually the sum of squares that represents the variation among the different samples. And sum of squares within and is denoted SSW. It is the sum of squares that represents the variation within samples that is due to chance. So in order to get to these formulas, we need to know about this sum of squares between and within, because the formula for the mean square between, it's actually sum of squares between divided by the degrees of freedom of the numerator, while the mean square within is sum of squares within divided by degrees of freedom of the denominator. However, we will need to know these formulas only to complete a summary table, ANOVA summary table. But to do a test, we will be using the calculator, and we will do the test using the p-value method. We will practice with all of this in this video. So we will focus first on making sure we know that the p-value is the one that we are looking at when we are trying to do or to conclude an ANOVA test or any test. This test is always right-tailed, and this test is done as simple as the other test. You will see the test ANOVA under test, but before completing this, you want to make sure that you enter in list the values that you are given in the problem. So you will have list, you will enter the values, and then you will perform an ANOVA. As soon as you perform the ANOVA, the F, the statistic, will appear, and the p-value will also appear, and you will be able to conclude and interpret your finding. Before that, though, we will be practicing with a summary table for ANOVA based on these formulas that I just wrote down. So let's take a look at how a table like this looks like. So this is how an ANOVA summary table looks like. And this ANOVA summary table will be produced by any statistical software, okay? That's why we need to have a little bit of exposure to these formulas and understand what these formulas do. Now, variation between is also called the factor, and it is a categorical variable, while variation within is also called the error or the response, and it is a numerical variable. Sum of squares, we have two different types, between and within. Is a variable numerator on the top. The mean square between is actually sum of square between what's in here divided by degrees of freedom numerator, which is right here. Same thing for mean square within. We have a fraction line. On the top, we have the first number in this row, which is sum of square within. And on the bottom, we have degrees of freedom of the denominator. The test value formula is F equals MSB, mean square between, over mean square within. And the p-value is found by doing the ANOVA test, or we can use FCDF on the calculator. And I'll show you how to do that. Of course, you can add these two and come up with a summation here. And the same thing here, come up with a summation. You see that this part of the table is black, so we don't really have any values in there. So let's try to work a little bit with the table and try to see how we can find all of these values. And how do we use another distribution, which is FCDF? This is how we find the p-value. And to be more specific, I'll write it down right here that the p-value can be found using FCDF from the test value to E99. As I said, this is a right tail test, right? So it will be E99. But then since we have 2 degrees of freedom, we want to make sure we put in the degrees of freedom. And that's why we have it right here in the table. Besides the fact that those are part of the mean square between and mean square within. You just simply have to put this in here, and then you will find the p-value. The p-value will also be displayed as soon as you put in there or you run the ANOVA test. If you want to do it with a distribution with FCDF, this is how you do it. So let's just try to work a little bit with some summary tables. Knowing all of these formulas, we should be able to complete some problems. And don't be scared when we see something like this. So here is the ANOVA summary table. And remember, this is what's given. We have the sum of squares between. In other words, we have the factor, and then we have the sum of squares within. We have the error or the response, degrees of freedom, numerator 2, and degrees of freedom, denominator 18. So to go ahead and figure out the mean square, just remember, and I'll write down the formula again, mean squares between is simply the first number divided by the second number. So for us, this will be 10.6667 divided by 2. And if you take a calculator and do so, we will get 5.33335. And this will be the mean square between. On a similar fashion, let's write down the formula for the other one. Mean square within will be this divided by this. The formula says sum squares within divided by degrees of freedom of the denominator. So in this situation, we have MSW equals 24.5714 divided by 18, and do the math. That will be 1.3651. Now to find the test value F, we can simply write down the formula MSB divided by MSW. So plug in the numbers and do the math, and we will have F equals 5.33335 and divided by 1.3651. Do the division, and you will have the F value. And the F value is 3.91. To find the p-value, we will use FCDF from the test value, which is 3.91 to E99, and we will simply plug in the 2 degrees of freedom. The first one is the numerator, which is 2. The second one is the denominator, which is 18. So let's do that using the calculator. Go to distributions, and let's take a look for FCDF. This is FPDF. We need FCDF, so it will be the next option. FCDF, hit enter, and you say from 3.91 to E99, or 10 raised to the 99 power. Degrees of freedom, as we said, was 2, and for the numerator and for the denominator was 18. And that's how we find the p-value. So in this case, by plugging that in, we have the p-value of 0.0389. And this is what we put right here on this table. So don't be scared when you see an ANOVA summary table, or when you have problems like this where you have to actually plug in values. As long as you know the relationship between those values, you should be fine. And now I'll just let you continue here and find the total. So this will be 34 point, or maybe 35 point something. Let you finish that. Just add those two to find the total. Add those two to find the total. That will be 20. Okay. Let's take a look at another problem. I have another example right here. So for this problem, we have to fill in the corresponding values. It seems that we do have a couple of values, but we need to find all of these other values. I can go ahead and come up with the mean square within, because I do have the test value, which is this number, and I do have the mean square between. This is the mean square between. And the question is, what is the mean square within? So this is just simple math, because I know F, it's actually mean square between over mean square within. So I can find this one. I can also find this piece right here, just because I know the formula right here, which is this number divided by degrees of freedom of the numerator. So I can find that. And of course, I can identify K and N after I'm done with all of this. Let's go ahead and do the first thing right here. Let's just find the mean square within. I'll just do the calculation on the side. Just by plugging in the formula, I will say F, which is 7.6277, equals MSV, which is 0.9607 divided by MSW. So to solve for MSW, I will simply cross multiply and then, of course, divide by that number, which is 0.9607 divided by 7.6277. So use a calculator to do so. And let's see what we get for MS within. Simply divide 0.9607 by 7.6277. And by doing so, I get 0.1259. Let's just round to 4 decimal places. And I put the answers with these colors, 0.1259. So this is the first answer that I get right here. Let's go ahead and find some other answers. Now I'm trying to find this answer right here, degrees of freedom of the numerator. I know that MSV, and let's write down the formula, equals SSV divided by degrees of freedom numerator. So I know this is SSB and I know this is MSB. So just plugging in, I should be able to find my answer. So let's just get rid of this now. I don't need this. I already found it. And I'll be left only with this formula, and I'll be using a different color to find this value right here. So I'll be plugging in this number for MSB, and I'll be plugging in this number for SSB, because this number is actually SSB. Let's do the work on a side. So I have MSB equals SSB divided by degrees of freedom of the numerator. 0.9607 equals to 0.8820 divided by degrees of freedom of the numerator. So by doing cross multiplication, solving this problem, we have 2.8820 divided by 0.9607. And let's see what we get for that value. So let's grab the calculator and do that division. And the answer is 2.9999. We can actually simply round that to 3. Because these are degrees of freedom, we need integers. Now the same thing and the same idea goes for degrees of freedom of the denominator. Right here we have this number, which is mean square within. The formula for the mean square within is SSW divided by degrees of freedom of the denominator. This part right here is sum square within, and this will be what we are looking for. So we will simply repeat the same thing, just change the numbers and of course the notations, and solve again for degrees of freedom of the denominator. Let's do so. So this one will change to W. As long as this one changes to denominator, I have the numbers mean square within was 0.1259 and sum square within is 4.5240 divided by degrees of freedom denominator. So to solve for this one, again, I will divide 4.5240 by 0.1259. So let's see what this number will be. So in this case, we have 35.93. This is again a degrees of freedom. So it should be an integer. I will round it to 36. So now we have the degrees of freedom right here, and that will be 36. You see that this matches up with this. So we could have just found it by subtracting from 39, the 3 that we found first, but we want to make sure that everything matches up. I'll let you add these two, which will be more than 7. Okay, so please do so. And the only thing that's left to do now is to find the p-value. I have all it needs to find the p-value, and I'll just write it down here. How do we find the p-value? Using the F distribution, p-value is FCDF from test value F, which is 7.6277 to E99. And don't forget to put the 2 degrees of freedom, the numerator first and the denominator last. And use the calculator to find that. We go to distributions, which are second bars. So next option after 9, it's FCDF. Hit enter and enter the values 7.6277. Upper it's E99, degrees of freedom 3, and degrees of freedom for the denominator 46. And hit enter. This is a very small p-value. You can see it's E-4 here, so round it to the first non-zero digit, it will be 0.123, and round it to 5. This will be p-value, and I'll just put it down here. So this is how you analyze or you come up with values in an ANOVA summary table. One more thing, you can see that right here they ask us, okay, what is K and what is N? Just remember, K is actually the number of individual samples of groups, and N is the total sample size. But how do I find this? If you recall that the degrees of freedom for the numerator was K minus 1, and you do have the degrees of freedom for the numerator, which is 3. 3 is K minus 1. Well, just by solving this, right, adding 1 to both sides, you can see that K is 4, right? So this is how many groups we have for this problem. And now how do we find N? Well, if you recall the formula for degrees of freedom of the denominator, it is actually N, capital N, minus K. Degrees of freedom for the denominator are right here on the table, so that will be 36. Will be N minus, and K we just found, which is 4. So now adding 4 to both sides, you'll get N equals 40. Let's now go ahead and do an ANOVA test. Here is the example. Government salary. The table shows the salaries in thousands of dollars of randomly selected individuals from the federal, state, and local levels of government. At alpha 0.01, can you conclude that at least one mean salary is different? So reading this problem, you know that you have to compare mean salary for 3 different groups, which will make you think I have to do an ANOVA test. So let's write down the given information. We have data, which is in tables, in one table, right? And we have alpha 0.01, and we have to answer this question. Can we conclude that at least one mean salary is different? Well, how many mean salaries do we have? Well, it seems that we have 3 groups, so we'll have 3 mean salaries, which will make us think I have to do an ANOVA test. Let's set up the test, okay? Because I have the table right here, I'll set up the test around it. We will go through this step by step. So step 1, H sub 0, H sub A. H sub 0, this means salaries are all equal to each other, and 2, at least one mean salary is different. You know, this is a right tail test. This is the claim. ANOVA, it's always a right tail test. Step 2, what distribution do we use? Well, we use the F distribution. F distribution comes to 2 degrees of freedom. Degrees of freedom of the numerator, which is the formula K minus 1. Degrees of freedom of the denominator follows the formula N minus K. So how many groups do we have? We have 3. So this one will be 3 minus 1. This one will be 2. How many values do we have total? Well, if you look at this table, we have 10 in each. So we'll have 30 minus K, which is 3. We'll have 27. So these are the 2 values, and we will simply be doing the ANOVA. How do we do ANOVA test? By starting with entering these values in 3 lists. Let's do so, and then we will have the results, and we'll write down the F, which is the test statistic, and the p-value, and we'll be able to conclude the test. I already entered these values in pre-list. You may want to stop the video and enter the values too, and then come back. This takes some time. So here we go. You have the values in the list. Go to step, go to test, and pick ANOVA. ANOVA is the last one right here, so use arrows to get there. Hit enter, and you simply have to say, do this for the three lists. Second one, comma, second two, comma, second three. Hit enter, and here you'll have the results. So F is 21.99, and the p-value is a very small p-value. So I'll just round it to 0. And now we're ready to conclude the test. So I'll just say right here, p-value of 0 is less than or equal to 0.01, which means I will reject the null hypothesis. And the last step, I will say at alpha equals 0.01, there is enough evidence to support the claim, or I'll just simply copy this down. So at alpha equals 0.01, there is enough evidence to conclude that at least one mean salary is, and that's how we do an ANOVA. There is another example right here, and let's do that. Random sample of enrollments from public institutions of higher education learning with enrollments under $10,000 is shown. As you can see, we have West, Midwest, Northeast, and South. This list don't have to have the exact same number in it. You see, this one is longer, and that's okay. At alpha equals 0.10, test the claim that the mean enrollments are the same in all parts of the country. Assume the populations are normally distributed with the same variance. So this is something that we assume when we do an ANOVA test. It should be stated in the problem. The first thing I ask you to do is put these values in list 1, list 2, list 3, and list 4, and then we will compare the results because I've already completed this problem. We will take a look at the answer. So make sure you have the exact same answer. You may want to stop the video and take the time to have all of these values in lists, and we will continue after that. Now that you have those lists in your calculator and you perform the ANOVA test, let's take a look at these results. First of all, don't forget you have to write down the hypothesis. So the first hypothesis was all of those means are equal. And the second hypothesis, or the alternative hypothesis, at least one of these means is different from the other. Now keep in mind the claim in this case was the top one, and this is a right tail test. After you did perform the ANOVA test, your test statistic value should have been 0.91, and the p-value, look at this, is 0.4502, which is a very large p-value. So your fourth step, which is making the decision based on the p-value method, should be fail to reject because p-value is greater than 0.10. We will not reject, which means there is insufficient evidence to reject the claim. Keep in mind the claim was H0. So you should have this stated at step 5. There is insufficient evidence to reject the claim that the mean enrollments are the same in all parts of the country. I hope you have the same results. And with this, I conclude the video. Thank you for watching.